Imagine you're doing some task at your home and suddenly the doorbell rings. You won't ignore it, right? You will pause, go answer it, and handle whatever's there, and then come back and continue where you left off. Your CPU does this thousands of times every second, and the mechanism behind it is called an interrupt. In this video, we are going to break down exactly what an interrupt is, how it works, and why your computer cannot function without it. One way for your CPU to check if any device needs its attention is to constantly ask, is the keyboard ready? No. Is the disk done? No. Is the network ready? No. Is the keyboard ready again? Still no. This process is called polling, and as you might have observed, it is not very efficient. CPU wasted many cycles without doing any meaningful work. Interrupts flip this model completely. Instead of CPU asking devices, devices notifies the CPU when something happens. So, what exactly is an interrupt? It's a signal sent to the CPU that says, stop whatever you're doing, something important just happened and it needs your attention. You need to handle it now without any delay. This signal can come from three places: hardware, like a keyboard press, a mouse click, or a disk finishing a read; software, a running program explicitly requesting operating system services; or the CPU itself when it detects something like a division by zero or an invalid memory access. In all these cases, the CPU pauses its current work, deals with the interrupt, and resumes whatever it was doing before it got interrupted. This all of this happens so seamlessly that your running program never even knows that it was stopped in between. Let's take one example and try to understand what happens when you press a key on your keyboard. Step 1. The keyboard controller detects the key press and sends an interrupt signal to the CPU. Step 2. The CPU finishes the single instruction it was working on, and not the whole task, just one instruction. Step 3. The CPU saves its current state, like program counter, registers, flag. This is called saving the context. Step 4. CPU looks up the interrupt vector table to find which handler function is responsible for this interrupt. Step 5. It jumps to that handler, like called the interrupt service routine, and executes it. Step 6. Once done, the CPU restores the saved context and resumes exactly where it left off. The running program never even knows that anything happened and it just resumes smoothly. So, how does the CPU know which handler to run for each interrupt? OS maintains something called an interrupt vector table for this purpose. It is a lookup table which maps an interrupt number to the memory address of the corresponding handler function. Interrupt 14, that's the page fault handler. Interrupt 32, timer. Interrupt 33, keyboard, and so on. You get the idea, right? When an interrupt fires, the CPU looks up the number, finds the address, and jumps directly to the right code that it needs to execute. There are essentially four different types of interrupts. First one is hardware interrupts, triggered by physical devices, keyboard press, mouse click, network packet arriving, disk IO completing. These are the classic interrupts what most people think of. Next is timer interrupts, fired by the system clock every few milliseconds. This one is special because it's the heartbeat that drives preemptive multitasking, which we will get to in a moment. Next is software interrupts, triggered by a running program using special int instruction. This is how user applications request services from the operating system, like file reads, memory allocation, and so on. And finally, exceptions or traps, which are raised by the CPU itself when something goes wrong, like division by zero, accessing an invalid memory, a page fault. The CPU flags it and the OS decides what to do. When an interrupt fires, the code that actually runs is called an interrupt service routine or ISR. ISRs are written by OS kernel developers or device driver authors. They run in kernel mode, that is the highest privilege level, which means they have full access to the hardware. So, a buggy ISR code can crash the entire system. So, this is like a serious low level code. Now, golden rule for ISRs is to be fast and do minimum possible operation and then exit. To achieve this, ISRs are split into two halves. The top half runs immediately, reads data from the hardware, acknowledges the interrupt, schedules the rest of the work. The bottom half runs later when the system is in a safer state, doing the heavier processing like parsing a network packet or waking up a sleeping process. This split keeps the system responsive even under heavy interrupt load. Not all interrupts are equal. The system assigns priority levels. A hardware error gets a higher priority than a timer, which gets higher priority than a keyboard press. If a higher priority interrupt fires while a low priority ISR is running, it can interrupt that ISR. This is called nested interrupts, as you are interrupting an interrupt. The OS can also temporarily disable interrupts entirely. This is called masking. It is used when the kernel is doing something very critical that must not be interrupted midway. Masking is always kept very short because when interrupts are masked, the system is essentially blind to everything happening around it. So, why does all of this matter? Because interrupts are the foundation of almost everything your computer does. Preemptive multitasking? That's the timer interrupt firing every few milliseconds, which lets the OS switch between processes, which in turn gives you the illusion that multiple programs are running simultaneously. Efficient IO? The CPU starts a disk read, then goes off and does other useful work. When the disk is done, it fires an interrupt. CPU spent no time polling, so no wasted cycles. System calls? Every time your program reads a file or allocates memory, it's using a software interrupt to safely cross from user mode to OS kernel. And the error handling? When your program crashes with a segmentation fault, that's a CPU exception interrupt being caught by the OS, which then terminates the process gracefully. Let's recap everything quickly. Polling wastes CPU cycle. Interrupt lets devices notify the CPU instead. The CPU pauses, saves its context, runs the ISR, restores context, and resumes. The IVT interrupt vector table maps interrupt numbers to handler address. There are 4 types: hardware, timer, software, and exceptions. ISRs are fast kernel mode functions split into top and bottom halves. And interrupts are the foundations of multitasking, IO, system calls, and error handling. That's it for today's video. I hope this video helped you in getting a fair understanding about interrupts, what they are, why they exist, and how they work. If yes, then please give this video a like. Comment down if you have any questions or if you want me to cover any other topic. And subscribe for more such content. See you in the next one.